In August of 2024, a single point of light appeared in an image where nothing was supposed to be. It sat beside the nearest sun-like star to our own, hiding in a glare so violent that no telescope in history had ever been able to see past it. For decades, that glare had been an impenetrable wall, swallowing whole any faint companion that might be orbiting there, defeating every instrument we aimed at it. And then, for the first time, something slipped through. Then, when astronomers went back to look again, it was gone. They returned a second time, and still nothing. A point of light that appeared in one image vanished in the next. And then, when they dug back through older data from a completely different telescope, seemed to have been there years earlier as well. A world that shows itself and then hides again and again, as if it does not want to be found. This is why the closest star system to Earth has become the most frustrating, the most thrilling, and the most quietly unsettling target in modern astronomy. Because what James Webb may have glimpsed there is not just another distant world, but a planet that seems to vanish every time we try to confirm it exists. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. Look up at the southern sky on a clear night, far from any city, and somewhere along the faint river of the Milky Way there is a single bright point that most people walk past without a second thought. It does not flicker with any special drama. It does not pulse or shimmer in colors that catch the eye. It is simply there, third brightest of all the stars you can see, steady and golden and almost ordinary. And yet that point of light is the closest stellar neighbor we have. It is the nearest doorway out of our own solar system, the first stepping stone on any imaginable journey beyond the sun. Its name is Alpha Centauri. For most of human history, it was just a star, a bright one, yes, important for navigation, woven into the myths of every culture that ever looked south and wondered. But a star and nothing more. We had no way of knowing what surrounded it, no way of asking whether other worlds circled that distant fire, the way our own world circles the sun. That question stayed locked away, untouchable, for thousands of years. Now, for the first time, we are beginning to pry it open. And what we are finding is stranger than anyone expected. To understand why this matters so much, you have to understand just how close Alpha Centauri really is. In the vast emptiness of the cosmos, almost everything is unimaginably far away. The light reaching your eyes from most stars left them centuries ago, sometimes millennia ago, traveling across distances so enormous that the numbers stop meaning anything. But Alpha Centauri sits just over 4 light-years from Earth. That is roughly 40 trillion kilometers. It is still a staggering distance, far beyond anything we could ever hope to cross with the machines we have today. And yet, in cosmic terms, it is practically next door. If you shrank the entire Milky Way galaxy down to the size of a continent, the gap between our Sun and Alpha Centauri would be smaller than the length of your hand. It helps to dwell on that number for a moment, because 4 light-years is one of those distances that sounds almost manageable until you actually try to picture it. Light is the fastest thing in the universe. In a single second, a beam of light travels nearly 300,000 kilometers, enough to circle the Earth more than 7 times in the span of a single heartbeat. That same beam of light reaches us from our own sun in about 8 minutes. It reaches us from the outer edges of our solar system in a matter of hours. But to cross the gap between the sun and Alpha Centauri, that same beam of light, never slowing, never stopping, would have to travel for more than 4 years. The light leaving Alpha Centauri tonight will not arrive at Earth until a child born this evening is walking and talking. And that is the nearest star system we have. Now consider what that means for any physical journey. The fastest spacecraft humanity has ever built, machines flung outward by the gravity of giant planets and the fury of rocket engines, travel at speeds that would have seemed magical to our ancestors. And yet, at those speeds, a journey to Alpha Centauri would take tens of thousands of years. We are talking about a voyage longer than the entire span of recorded human civilization, just to reach the closest star to our own. This is the paradox of Alpha Centauri. It is impossibly close and impossibly far at the same time. Close enough to be our nearest neighbor, the obvious first target for every dream of leaving home. Far enough that, with the tools we have today, it remains hopelessly out of reach. That tension between nearness and distance, between the possible and the impossible, is part of what makes this star system so endlessly fascinating to us. Out of the 400 billion stars in our galaxy, this is the one we could reach first. This is the one that any future civilization, looking to leave the cradle of its home system, would aim for before anything else. And so, it has always carried a special weight in the human imagination. When we dream of interstellar travel, we dream of Alpha Centauri. When science fiction writers imagine the first ship to leave the solar system, they almost always send it there. It is the nearest shore on an ocean we have barely begun to understand. And it has been watching over the southern sky for as long as there have been eyes to look up. For the peoples of the southern hemisphere, Alpha Centauri has been a familiar companion for tens of thousands of years. It rides high in southern skies, one of the pointer stars that guides the eye toward the famous cross-shaped pattern used for navigation across oceans and deserts. Countless generations looked up at that golden light and wove it into their stories, never knowing that they were gazing at the closest doorway out of the solar system. They could not have known that the single bright point they saw was actually a pair of suns, locked together with a third faint ember circling far beyond. They could not have known that those suns might shelter worlds of their own. To them it was a light, a marker, a fixed and faithful presence in the turning sky. It is worth remembering, too, that whenever we look at Alpha Centauri, we are looking into the past. The light entering your eye from that star tonight did not leave it tonight. It left more than 4 years ago, and has been traveling across the emptiness ever since, crossing 40 trillion kilometers of vacuum to finally arrive at this moment. You are not seeing Alpha Centauri as it is. You are seeing it as it was 4 years ago. This is true of every star in the sky, and the farther away they are, the deeper into the past you are looking. Some of the stars you can see left their light behind centuries ago, others thousands of years ago. When you look up at a clear night sky, you are not seeing the universe as it is now. You are seeing a vast collage of different moments in the past, all arriving at your eye at once. Alpha Centauri, being so close, offers one of the freshest views available. A glimpse only 4 years old, and yet even that nearest, freshest light is a message from the past, a reminder that across cosmic distances, to look outward is always to look backward in time. There is something poetic in this when it comes to the candidate planet. The point of light Webb captured in 2024 did not show the planet as it was in 2024. It showed the planet as it was more than 4 years earlier, the light having spent all that time crossing the gulf between the stars. In a very real sense, when we study this world, we are studying its past, watching a delayed broadcast of a planet that has since moved on around its orbit. By the time we confirm it, if we ever do, the light we use will already be years old, a snapshot of a moment that has long since passed out there in the dark. This is the strange intimacy of astronomy. We reach across enormous distances, but only ever touch the past. But here is where the story takes its first surprising turn. Alpha Centauri is not a single star at all. When you look up and see that one bright golden point, you are actually seeing the blended light of two stars locked together, orbiting one another in a slow gravitational dance that has continued for billions of years. The first is called Alpha Centauri A. It is remarkably similar to our own Sun, almost a twin. It has nearly the same mass, nearly the same size, nearly the same temperature, and it shines with that same warm yellow light that has nurtured life on our planet for so long. This resemblance is not a trivial detail. Among all the nearby stars, true matches for our Sun are not especially common. Many of our stellar neighbors are small, cool red dwarfs, quite different from the Sun in size, temperature, and behavior. Others are larger or hotter, or older or younger, each difference changing the kind of light they pour out and the kind of environment they would create for any planets around them. Alpha Centauri A, by contrast, is about the same size as the Sun, about the same age, and about the same temperature. It is, in many ways, the closest thing to a true solar twin in our immediate cosmic neighborhood. That makes any planet found around it especially interesting, because such a planet would be bathed in light very much like the light Earth receives, warmed by a star very much like the one we orbit. If you could stand on a world orbiting Alpha Centauri A, the daylight would feel eerily familiar. The light would be that same warm, golden white that we know from our own sky, falling on the landscape with a familiar gentleness, because Alpha Centauri A pours out light remarkably similar to our Sun's. But the sky above such a world would hold one breathtaking difference. There would be a second sun. Alpha Centauri B, the companion star, would hang in that sky as a second brilliant point, far brighter than any star but not as overwhelming as the main sun, depending on where the two stars were in their long mutual orbit. At times it would shine as a dazzling second light in the daytime sky. At other times, when the geometry was right, it might rise or set separately, casting its own glow across the land, perhaps tinting the twilight with a second set of shadows. A double sunset, two stars sinking toward the horizon together or one after the other, painting the sky in layered colors. It is one of the most evocative images in all of astronomy, and it may be more than just imagination. If a planet truly orbits Alpha Centauri A, then somewhere out there, 4 light-years away, that double-sun sky is real. The second star is Alpha Centauri B. It is a little smaller, a little cooler, glowing with a slightly more orange hue. These two stars circle each other at a distance that varies over their long orbit, sometimes drawing as close as the gap between the Sun and Saturn, sometimes swinging out much farther. They are bound together, partners in a celestial waltz that takes about 80 years to complete a single turn. And then, far off to the side, much farther out, there is a third member of the family. A tiny, dim, red ember of a star called Proxima Centauri. It is so faint that you cannot see it at all with the naked eye, despite the fact that it is, by the smallest of margins, the very closest star to our Sun. Proxima drifts in a vast, slow orbit around the central pair, so distant from them that it takes hundreds of thousands of years to circle them once. It is worth pausing on Proxima for a moment, because it tells us something important about how strange and varied stars can be. Proxima Centauri is what astronomers call a red dwarf, the most common type of star in the entire galaxy. It is small, perhaps an eighth the mass of our Sun, and it burns cool and slow and red, where our Sun is a roaring furnace that will exhaust itself in roughly 10 billion years. A red dwarf like Proxima sips its fuel so gently that it could keep glowing for trillions of years, far longer than the current age of the universe itself. These small red stars are everywhere. The vast majority of stars in the Milky Way are red dwarfs, faint and quiet, and easy to overlook, and Proxima, our closest stellar neighbor of all, is one of them. It is also known to host its own planets. Astronomers have found 3 worlds orbiting Proxima Centauri, including one that sits in the star's habitable zone. But red dwarfs are temperamental hosts. They are prone to violent flares, sudden eruptions of radiation that can blast their nearby planets, stripping away atmospheres and bathing any potential surface in harsh bursts of energy. So while Proxima's planets are tantalizing, they come with serious complications for the question of whether anything could live there. A flaring red dwarf is a harsh parent, prone to lashing its nearby worlds with sudden bursts of radiation that could strip away atmospheres and scour their surfaces. A planet huddled close to such a star, as it would have to be to stay warm, sits directly in the line of fire. This does not rule out life around red dwarfs, but it does make their worlds a more complicated and uncertain prospect. The 2 bright central stars, Alpha Centauri A and B, are a different story altogether. They are sun-like, stable, mature, the kind of stars that have nurtured life in at least one known case, our own. And that is precisely why they have always been the more alluring targets in the search for another Earth-like world. A planet around a calm, sun-like star feels closer to home than a planet huddled against a flaring red dwarf. Together, these 3 stars form a triple system, a small gravitational community traveling through the galaxy as one. And every one of them, in principle, could host planets. This is the prize that has drawn astronomers to Alpha Centauri again and again. A sun-like star, right next door, possibly surrounded by worlds we could one day study in extraordinary detail. The faint red dwarf of the system, Proxima Centauri, has already yielded planets. 3 of them confirmed to orbit that small, cool star, including one in its habitable zone. Those discoveries were made through the indirect methods, by detecting the gentle tug of the planets on the star. But the 2 bright sun-like stars at the heart of the system, Alpha Centauri A and B, had stubbornly refused to give up any confirmed worlds of their own. For all the searching, all the campaigns, all the telescope time devoted to them, they remained frustratingly silent. It was a strange situation. The dim little red star had revealed its planets, while its 2 brilliant, sun-like companions, the more promising hosts in many ways, kept their secrets locked away. That is what made the possibility of a planet around Alpha Centauri A so enticing and so maddening. If there were a planet there, in the right orbit, at the right distance from its star, it could be the most important discovery in the history of the search for life beyond Earth. Not because it would be the only such planet, but because it would be the closest. Close enough to study. Close enough, perhaps, one distant day, to visit. This search, the search for another world like our own, is one of the oldest and deepest of all human questions, even if we have only recently gained the tools to pursue it seriously. For thousands of years, people have looked up and wondered whether the lights in the sky might be other suns, and whether those suns might have worlds, and whether those worlds might hold life. It was a question that could only be asked, never answered. A matter of imagination and longing rather than evidence. But in our own era, that has changed. We now know, beyond any doubt, that the stars are other suns. We now know that planets are common, that the galaxy is filled with them, and we now have, for the first time, telescopes powerful enough to begin examining individual worlds around individual stars, to ask not just whether planets exist, but what they are actually like. The dream of finding another Earth has moved from the realm of pure speculation into the realm of active, hands-on science. And in that search, the nearest sun-like star is the obvious first place to look. If we are ever going to find a familiar world, a place with the right temperature, the right kind of star, the right conditions for liquid water, it would be an extraordinary stroke of fortune to find it right on our doorstep at Alpha Centauri. For decades, that possibility hung in the air, tantalizing and just out of reach. The problem was not a lack of interest. The problem was that finding planets around these stars turned out to be one of the hardest things in all of observational astronomy. To understand why, you have to understand how astronomers usually find planets around other stars in the first place. Most of the thousands of worlds we have discovered beyond our solar system were never actually seen. Not directly. We did not take their picture. Instead, we detected them through their effects on the stars they orbit. One method watches for tiny dips in a star's brightness. When a planet passes directly between us and its star, it blocks a sliver of that starlight, causing the star to dim by a minuscule amount. If we measure that dimming carefully, we can deduce that a planet is there, even though we never see it. The amount of dimming is astonishingly small, often a fraction of a percent, a barely perceptible flicker in the star's steady glow. But it is regular, repeating each time the planet completes an orbit and passes in front of its star again. From the depth of the dip, we can estimate the planet's size. A bigger planet blocks more light. From the timing between dips, we can work out the length of its year. This is how the great planet-hunting space telescopes found most of their worlds, staring at hundreds of thousands of stars at once, watching for those faint, regular flickers. Another method watches the star itself for a subtle wobble. A planet does not simply orbit a star. The planet and the star both orbit their shared center of mass. A massive planet tugs its star back and forth ever so slightly as it circles, and that tiny motion shifts the color of the starlight in a way we can measure. A wobble toward us, a wobble away, repeating like clockwork. From that rhythm, we can infer the presence and the mass of an unseen world. This wobble method was, in fact, how the very first planets around sun-like stars were discovered back in the closing years of the 20th century. Astronomers watched a star and noticed that its light was rhythmically shifting, ever so slightly, toward the blue and then toward the red, over and over in a steady cycle. That shifting was the fingerprint of an unseen planet, tugging its star back and forth as it orbited. It was a triumph of precision, detecting motion so tiny that the star was moving at no more than the speed of a person walking, across distances of trillions of kilometers. The technique has since been refined to astonishing sensitivity, capable of detecting the gentle pull of ever smaller planets. But it has a fundamental requirement. The star must be calm and well-behaved enough for that delicate rhythm to be picked out. And there lies the trouble with Alpha Centauri. Both of these techniques are brilliant, and together they have revealed nearly 6,000 confirmed planets across the galaxy. It is worth letting that number sink in. 6,000 worlds. Just a few decades ago, at the start of the 1990s, we knew of exactly 0 planets orbiting other sun-like stars. The planets of our own solar system were the only ones humanity had ever confirmed to exist. For all of history before that, the existence of other worlds around other stars was a matter of pure philosophy and faith, a reasonable guess, but nothing more. Then, one by one, the discoveries began. A strange world here, orbiting a dead stellar remnant, a scorching giant there, whipping around its star in a matter of days. And then the floodgates opened, as new telescopes and new techniques turned a trickle of discoveries into a torrent. Today we know that planets are not rare at all. They are everywhere. On average, nearly every star in the sky has at least one planet, and many have whole families of them. Our galaxy alone likely contains hundreds of billions of worlds, a number so large it defies any attempt to truly grasp it. We went, in a single human lifetime, from knowing of no planets beyond our own system to knowing that the galaxy is overflowing with them. And yet, despite all of that progress, despite 6,000 confirmed worlds, the planets around Alpha Centauri A and B remain stubbornly hidden. The closest sun-like stars to Earth, the most natural place to look, were among the very hardest to crack. Both of these techniques struggle terribly when it comes to Alpha Centauri. The wobble method needs the star to sit still enough that its tiny planetary tug can be picked out from all the natural noise of a churning, boiling stellar surface. But Alpha Centauri A and B are locked in their own gravitational dance with each other, and that mutual motion drowns out the far gentler tug of any planet that might be there. The two stars swing around each other with a motion far larger and more powerful than any planetary wobble, and disentangling the faint signal of a possible planet from the overwhelming gravitational waltz of the two suns is extraordinarily difficult. It is like trying to detect the gentle sway of a small boat tied to a ship that is itself heaving on the open sea. The larger motion swamps the smaller one. The dimming method needs a planet to pass directly across the face of its star from our point of view, and the geometry simply has not cooperated. For a planet to be caught dimming its star, its orbit has to be aligned almost perfectly edge-on as seen from Earth, so that the planet's path carries it directly between us and the star. Most planetary orbits are not tilted at just the right angle for this to happen, and around Alpha Centauri, the alignment has not delivered the neat, repeating dips that the dimming method relies on. So both of the great workhorse techniques, the ones responsible for the vast majority of all known planets, came up empty against our nearest neighbor. So astronomers were left with a third, far more difficult approach: direct imaging. Actually taking a picture of the planet itself. And this is where the true scale of the challenge reveals itself. Imagine trying to photograph a firefly hovering next to a lighthouse. The lighthouse is blindingly bright, its beams sweeping across the water, flooding everything around it with light. The firefly is impossibly faint by comparison, a tiny flicker lost in that overwhelming glare. Now move the whole scene tens of thousands of kilometers away, until the lighthouse and the firefly are so close together in your view that they almost merge into a single point. That is what astronomers face when they try to photograph a planet next to a star. To make the comparison sharper still, picture standing in one city and trying to photograph a single candle flame held right beside a brilliant searchlight in a city on the far side of a continent. The searchlight and the candle would blur into one impossibly tiny, impossibly bright dot, and the candle's faint glow would be utterly lost in the searchlight's blaze. Separating those 2 points of light and pulling out the candle's feeble flame is roughly the scale of the challenge. The star can be billions of times brighter than the planet beside it. Stop and consider what a billion times brighter actually means. If the planet were as bright as a single candle, the star beside it would shine with the light of a billion candles, all crammed into nearly the same spot in your field of view. The faint glow of the candle does not just get lost. It gets utterly obliterated, swallowed whole by the blazing light next to it. The light from the star spills out, scatters, floods the detector, and buries any hint of the faint world hiding in its glow. For most of the history of astronomy, this was simply impossible. The technology did not exist to separate that whisper of planetary light from the roar of the star. And it was not only a matter of brightness, it was also a matter of resolution, of being able to tell 2 points of light apart when they sit extremely close together in the sky. From our vantage point, a planet and its star are separated by only the tiniest sliver of angle, far smaller than anything the human eye could ever distinguish. To pull them apart, you need a telescope with extraordinarily sharp vision, an instrument capable of resolving detail at the absolute limits of what physics allows. For ground-based telescopes, there is an additional enemy: the atmosphere itself. Earth's air is constantly churning and shifting, and that turbulence smears and blurs the light of the stars before it ever reaches the telescope. It is the same effect that makes stars appear to twinkle. That twinkling is beautiful to look at, but for an astronomer trying to capture a faint planet, it is catastrophic. It blurs the sharp point of starlight into a restless, shimmering blob, drowning any nearby planet even further. This is one of the great reasons to put telescopes in space, above the atmosphere entirely, where the light arrives clean and steady and unblurred. And Alpha Centauri made the problem even worse, because there was not one blinding lighthouse but two, sitting close together, each one flooding the field with its own overwhelming light. Even when you managed to block out one star, the second one was still bright enough to drown everything. This is why, for so long, the nearest sun-like stars remained, in a sense, the hardest of all to truly explore. The closest worlds were hidden behind the brightest glare, and then came a telescope built to see what no instrument before it could. The James Webb Space Telescope was not originally designed to hunt for planets around Alpha Centauri. When engineers spent decades building it, their dream was to look far in the other direction, toward the most distant galaxies in the universe, the faint smudges of light that left their sources more than 13 billion years ago, in the first chapters of cosmic history. Webb was meant to peer back to the dawn of the stars themselves. This was a project of almost unimaginable ambition and patience. It took decades to design and build, the work of thousands of engineers and scientists across many nations, an international collaboration on a truly grand scale. It cost enormous sums and survived years of delays, technical setbacks, and moments when its future hung in doubt. Its design was breathtakingly bold, a telescope too large to fit inside any rocket in its final form, and so it had to be folded up like a piece of cosmic origami, packed tightly away, and then unfolded automatically once it reached space, executing hundreds of intricate steps with no possibility of repair if anything went wrong. When it finally launched and began that long, nerve-wracking sequence of unfolding, the entire community of astronomers held its breath. Any single failure among those hundreds of steps could have doomed the mission. But step by step, the great mirror unfolded, the vast sunshield stretched out, and the telescope came to life exactly as intended, settling into its distant outpost and opening its golden eye on the universe. It was one of the most complex and successful scientific instruments ever built, and almost immediately it began transforming our view of the cosmos. In the time since it opened its eye, Webb has peered deeper into the universe than any telescope before it, capturing light from galaxies that formed in the first hundreds of millions of years after the universe began. It has dissected the atmospheres of distant planets, sniffing out the chemical makeup of worlds trillions of kilometers away. It has stared into the glowing nurseries where new stars are being born and watched the slow death throes of old ones. It has rewritten textbooks and raised new questions faster than anyone expected. And then, in a use its builders barely dared to anticipate, it turned its gaze on the nearest sun-like star and attempted something at the very edge of its abilities, to capture the faint light of a planet hidden in a brutal glare just 4 light-years away. To do that, it was built to detect infrared light, the kind of light our eyes cannot see, the kind that carries the faint heat signatures of objects across enormous distances. It was given a gleaming golden mirror, more than 6 meters across, the largest ever flown in space, folded up like origami to fit inside its rocket, and then unfurled once it reached its lonely outpost far beyond the moon. It was wrapped in a vast sunshield the size of a tennis court, chilling its instruments to within a few degrees of the coldest temperature physically possible, so that its own warmth would not blind it. That detail deserves a moment of its own, because it captures just how extreme this machine really is. Everything in the universe that has any warmth at all glows faintly in infrared light, including the telescope itself. If Webb's instruments were even slightly warm, that warmth would flood its own detectors, like trying to photograph a candle flame while your camera is on fire. So the telescope had to be made unimaginably cold. It sits in permanent shadow behind its sunshield, far from the warmth of Earth, chilled down to roughly 230 degrees below zero on the Celsius scale, only a few degrees above absolute zero, the coldest anything can ever be. At that temperature, the telescope falls silent in the infrared, its own heat glow extinguished, so that it can finally hear the faint whispers of warmth coming from across the universe. It was placed not in orbit around Earth, but at a special point in space well beyond the moon, more than 1,000,000 kilometers away, where it could keep the sun, the Earth, and the moon all behind it at once, hiding from their light and heat. From that lonely outpost, it stares outward into the dark, gathering light that has traveled for almost the entire age of the universe to reach it. Everything about Webb was engineered for one purpose above all: to see the faintest possible heat glowing in the darkness. But it turns out that the very same abilities that let Webb see ancient galaxies also make it extraordinary at something its builders barely dared to hope for: seeing the faint warmth of a planet next to a brilliant star. Because a planet, even a cold one, glows in infrared light. It radiates heat, whether from the warmth of its own formation or from the starlight it absorbs and re-emits. And in the infrared, the brightness gap between a star and a planet shrinks. The star is still far brighter, but not by quite as crushing a margin as invisible light. This is one of the great secrets of infrared astronomy, and it is worth understanding why it works. In visible light, the kind our eyes detect, a star is staggeringly brighter than any planet near it. Stars are hot, and hot objects pour out enormous amounts of visible light, while planets shine in visible light mostly by reflecting a small fraction of their star's glow. The contrast is brutal. A planet can be many billions of times fainter than its star, but in the infrared, the situation softens. A planet, warmed by its star or by the heat left over from its formation, glows with its own infrared light it produces rather than merely reflects. Meanwhile, the star, though still bright, does not dominate the infrared quite as overwhelmingly as it dominates the visible. The result is that the gap between star and planet narrows, sometimes dramatically. It is still an enormous challenge. The planet is still vastly fainter, but the odds shift in the astronomer's favor. This is why a telescope built to see infrared light, like Webb, is so well suited to the hunt for planets that would be utterly invisible in ordinary light. By looking in the realm of heat rather than the realm of visible color, Webb gives faint, warm worlds a chance to reveal themselves. Webb also carried a special tool, an instrument called the mid-infrared instrument, designed to capture the longest wavelengths of infrared light, the deep heat glow of cool objects. And built into that instrument was something remarkable: a coronagraph. A coronagraph is, at its heart, a beautifully simple idea. It is a tiny mask placed precisely inside the telescope that blocks out the direct light of a star. Think of holding your thumb up to cover the sun so you can see the landscape around it without being blinded. The coronagraph does the same thing, but with extraordinary precision, hiding the overwhelming glare of the star while letting the faint surroundings shine through. With the star's light masked away, the region right beside it suddenly becomes visible, and anything faint lurking there has a chance to be seen at last. But a coronagraph is far more subtle than simply taping a dot over a bright spot. The light of a star does not behave like a tidy point that can be neatly covered. When starlight passes through any telescope, it bends and ripples around the edges of the mirror and its supports, spreading out into delicate patterns of rings and spikes. A crude mask would block the central glare but leave all that spilled-out light still flooding the surroundings. So, a real coronagraph is a precisely engineered system, shaped to suppress not just the bright core of the star, but as much of that scattered, rippling halo as possible. It is one of the most delicate optical tricks in all of astronomy, a way of carving a small pocket of artificial darkness right next to a blazing source of light so that something faint can finally emerge from hiding. This was the key. This was the tool that might finally let humanity look directly into the heart of our nearest stellar neighbor. But even with all of Webb's power, observing Alpha Centauri was not going to be easy. In fact, it would turn out to be one of the most demanding tasks the telescope had ever attempted. The two bright stars were a nightmare to deal with. They were dazzlingly bright, far brighter than the distant galaxies Webb was built to study, so bright that they threatened to overwhelm the instrument. They were extremely close together in the sky, their light constantly bleeding into one another. And because the whole system is so near to us, it appears to move across the sky faster than more distant stars, drifting noticeably as Earth swings around the Sun. This is a consequence of that same nearness that makes Alpha Centauri so precious. Distant stars appear almost frozen in place over a human lifetime, so far away that their motion across the sky is imperceptibly slow. But a nearby star, like a nearby object viewed from a moving car, slides across the background much more quickly. As the Earth travels around the Sun, our viewpoint shifts, and a close star like Alpha Centauri appears to trace a tiny path against the more distant stars behind it. It also has its own genuine motion through the galaxy, carrying it steadily across the sky year after year. For most observations, this drift is a minor detail. But for a telescope, trying to lock onto a precise spot, hold a coronagraph mask exactly over a star, and stare for a long time to catch the faintest possible glimmer beside it. A moving target is a serious complication. You cannot simply point and forget. You have to track, to compensate, to account for the fact that your target will not hold still. A target that is too bright, too tightly packed, and too quick to sit still. The team that took on this challenge had to design a completely custom observing strategy, a special sequence built from scratch for this one extraordinary target. Nothing about the standard approach would work. Webb had been designed and optimized to find the faint, distant galaxies at the edge of the observable universe. Objects that are dim and far away and hold relatively still. Alpha Centauri was the opposite in nearly every respect, dazzlingly bright, extremely close, and quick to move. Using a telescope built for the faint and the far to study something brilliant and near required the operations team to invent an entirely new way of working. They had to develop a bespoke sequence of observations, carefully choreographed, designed specifically for the unique demands of this one system. It was the kind of effort that goes far beyond simply pointing a telescope and taking a picture. It demanded creativity, ingenuity, and a willingness to push the instrument into territory it was never originally meant to explore. And the extra effort paid off, producing observations that captured the faint candidate where standard methods would almost certainly have failed. They had to account for the glare of not one star but two, carefully positioning the coronagraph to block the light of Alpha Centauri A, while wrestling with the persistent brilliance of Alpha Centauri B nearby. They had to subtract, with painstaking care, the complicated patterns of light that the telescope itself creates. Because even the most perfect telescope does not produce a clean point of light from a star. Its mirrors and their supports cause the light to interfere with itself, spreading into faint rings and spokes, like the diffraction pattern you might see around a bright streetlight on a foggy night. These patterns are predictable, but they are also full of false hopes, little knots and speckles of light that can masquerade as planets. So the team gathered reference images, built mathematical models of exactly how the telescope scatters light, and then carefully subtracted those patterns away, scrubbing the image clean to reveal whatever faint, genuine sources might be hiding underneath. This process is its own kind of art. To know what to subtract, you first have to know exactly what the telescope does to starlight on its own, with no planet involved at all. So astronomers observe other stars, ones not expected to have visible companions, and use them as templates, maps of the telescope's own fingerprint of rings and spikes and speckles. Then they take those templates and subtract them from the image of Alpha Centauri, removing the predictable patterns and leaving behind only what does not belong, only what cannot be explained by the telescope itself. It is a bit like trying to hear a single soft voice in a noisy room by recording the noise of the room when the voice is silent, and then subtracting that noise away, leaving only the voice behind. Done carelessly, this process can create false signals, ghosts that look like planets, but are really just leftover scraps of imperfectly subtracted light. Done carefully, it can reveal a genuine, faint companion that no other method could ever have exposed. It was an enormous, delicate, meticulous effort, and in August of 2024, when they finally processed the data and cleaned away the glare and the scattered light and the speckles and the noise, something remained, a single point of light. Sitting beside Alpha Centauri A, in a place where the masked-out glare should have left only darkness. A faint, lonely glimmer that refused to disappear no matter how carefully they cleaned the image. It was exactly the kind of signal they had hoped, almost dared not hope, to find. A possible planet orbiting the nearest sun-like star to Earth. To understand the weight of that, remember everything that had stood in the way. The crushing brightness of the two stars. The impossible closeness of planet and star in the sky. The constant motion of the target. The scattered light. The speckles. The ghosts. The endless ways the data could fool them. Every one of those obstacles had to be overcome at once, and even then, success was far from guaranteed. For the faint point of light to survive all of that, to emerge cleanly from the processed image and sit there beside Alpha Centauri A in a place where a planet could plausibly orbit, was something close to a small miracle of observation. The excitement in that moment is hard to overstate. For the first time, a telescope had peered into the glare of Alpha Centauri A and seen something that looked like a world. Not an inference from a wobble, not a deduction from a flicker of dimming starlight. An actual point of light, captured directly, sitting in orbit around our closest solar twin. Try to imagine being one of the scientists in that room, staring at the cleaned-up image as it finally emerged from months of painstaking work. You've spent countless hours wrestling with the glare of two brilliant stars, subtracting patterns, hunting through noise, fighting against every reason the universe had given you to expect nothing. And then, there it is. A single, stubborn point of light that refuses to go away, sitting exactly where a planet could plausibly orbit, around the very star that is the closest twin to our own sun in all the sky. In that instant, you are seeing something no human being has ever directly seen before. A possible world circling our nearest stellar neighbor. It is the kind of moment scientists spend entire careers hoping for and rarely find. If it was real, it would be extraordinary. But that word, if, would come to dominate everything that followed. Because in science, a single observation is never enough. One point of light, no matter how promising, could be many things. It could be a distant background galaxy that happened to line up behind the star. It could be a passing asteroid drifting through the foreground at just the wrong moment. It could be a subtle glitch in the detector, a flaw in the image processing, a speckle of scattered light that survived the cleaning process and disguised itself as something real. Each of these possibilities is a genuine danger, and the history of astronomy is littered with candidate planets that turned out to be none of these things, just illusions. A background galaxy is a particularly sneaky imposter. Far behind Alpha Centauri, at distances of millions or billions of light years, sit countless faint galaxies scattered across the sky. If one of them happens to lie almost exactly behind the star from our point of view, it can appear as a faint smudge of light right where a planet might be, masquerading as a companion world. The way to rule this out is patience. Because Alpha Centauri, being so close, drifts measurably across the sky over months and years. A real planet would travel along with the star, bound to it by gravity, moving as the star moves. A distant background galaxy would stay fixed, and the star would slowly slide away from it, exposing the deception. A passing asteroid or other object in our own solar system is another possibility. A nearby piece of rock or ice drifting through the field at just the wrong moment, briefly imitating a planet before moving on. And then there are the purely technical phantoms, the speckles and artifacts created by the telescope and the analysis itself, the false signals that careful processing is meant to remove but can never fully guarantee are gone. To be sure, you have to look again. You have to return to the same patch of sky and confirm that the object is still there, still in the right place, moving the way an orbiting planet should move. And so the team did exactly that. They went back. In February of 2025, Webb turned its golden eye toward Alpha Centauri once more, ready to confirm what it had seen. And the point of light was gone. There was nothing there. No planet, no glimmer, no faint companion beside the star. Just the empty darkness where their candidate world should have been. It was a gut punch. The kind of moment that can make a scientist's heart sink. After all the effort, all the careful planning, all the painstaking work to capture that first image, to return and find nothing, was a bitter result. The natural fear in that moment is that the original detection was never real, that the point of light had been an illusion all along, a ghost conjured by noise and imperfect processing. That fear is not paranoia. It is exactly the kind of skepticism good science demands. A single detection is always suspect, precisely because the universe and our instruments are full of ways to fool us. But perhaps, they thought, it was a fluke. Perhaps something about that particular observation had gone wrong. So they tried again. In April of 2025, Webb looked a third time, and once again, there was nothing. The point of light that had appeared so clearly in August had simply vanished, refusing to show itself in either follow-up attempt. 2 observations, months apart, and in both of them the candidate planet was nowhere to be found. By any normal standard, this should have been the end of the story. A single detection followed by 2 clean non-detections is usually a death sentence for a planet candidate. It strongly suggests the original signal was never real, just noise dressed up as discovery. The most natural conclusion would be to quietly set it aside and move on. In fact, this happens far more often than the public ever hears about. For every confirmed planet, there are countless tentative hints that flicker into view and then fade away, never to be seen again, written off as statistical flukes or instrumental quirks. The history of exoplanet research is littered with such ghosts, promising signals that dissolved under further scrutiny. The responsible thing, in most cases, is to let them go. But the team did not move on. Because something about this particular case did not quite fit the usual pattern of a false alarm. There was a clue buried in the past that made them pause. Back in 2019, years before Webb ever turned toward Alpha Centauri, a ground-based telescope had caught something tantalizing. The European Southern Observatory's Very Large Telescope, using an experiment specifically designed to search for warm planets around these nearby stars, had recorded a faint hint of something near Alpha Centauri A. At the time, it was inconclusive. A whisper, not a shout. Not enough to claim a discovery. That earlier search had been an ambitious effort in its own right. A special campaign that pushed a ground-based telescope to its absolute limits in an attempt to directly image any warm planet that might be orbiting in the habitable zones of Alpha Centauri A and B. It was a bold gamble, and it produced a tantalizing but ultimately ambiguous result, a faint signal that could not be confirmed and could not quite be dismissed. For years, that whisper from 2019 sat in the records, unresolved, neither proof nor disproof, just an intriguing maybe. But now, looking back, the team noticed something striking. The position of that faint hint from 2019 lined up remarkably well with the position of the point of light Webb had captured in 2024. Two separate telescopes, 6 years apart, using completely different instruments, had each seen something faint in roughly the same place beside the same star. That is a difficult coincidence to dismiss. Think about what would have to be true for this to be mere chance. Two entirely different observatories, one on the ground and one in space, one working years before the other, each plagued by its own separate sources of noise and error, would have had to independently produce a false signal in nearly the same spot next to the same star. That is not impossible, but it is unlikely. The more natural explanation is that both telescopes were catching glimpses of the same real object, a genuine planet, appearing in roughly the same region of its orbit on both occasions. And so, the team found themselves facing a genuine mystery. How could a planet appear in two observations, years apart, taken by entirely different telescopes, and yet refuse to show up in two more recent attempts? How could something be there in 2019, there again in 2024, and then completely absent in early 2025? One member of the team described the situation perfectly. They were faced, they said, with the case of a disappearing planet. And rather than throwing up their hands, they decided to treat that disappearance not as a failure, but as a clue. It is a subtle but crucial shift in thinking. The easy interpretation of two non-detections is simple. The planet was never there. But that interpretation has to explain away two separate sightings. The one from Webb in 2024 and the matching hint from the ground in 2019 as nothing but coincidence. The harder interpretation, that the planet is real but moved, has to explain why it was missed twice. And the beauty of that harder interpretation is that it is testable. A planet that is real and simply moved out of view must have followed a specific path, and that path makes definite predictions about where it was at each moment. So instead of asking only whether the planet was there, the team asked a deeper question. If the planet is real, what orbit must it be on for it to have appeared in 2019 and 2024 and to have vanished in early 2025? That question turned the disappearances from a problem into a source of information. Because a planet, after all, does not sit still. It orbits. It moves around its star, sometimes appearing far to one side, sometimes swinging around to the front, sometimes vanishing behind the star entirely from our point of view. What if the planet was real, and the reason it had disappeared was simply that it had moved? What if, in February and April of 2025, the planet had drifted into a part of its orbit where it was too close to the blinding star to be seen, lost once again in the very glare the coronagraph was trying to block. It was a bold idea, but to test it, they would need to do something that had nothing to do with the telescope at all. They would need to turn to mathematics and to the power of simulation. The team built computer models of the Alpha Centauri system, not just the stars, but the gravitational landscape around them, the invisible web of forces that would shape the path of any planet trying to survive in such a place. And this is where things get genuinely tricky, because Alpha Centauri is not a calm, orderly system like our own. It is a place of competing gravitational pulls. A planet orbiting Alpha Centauri A would not have the luxury of circling its star in peace. It would also feel the relentless tug of Alpha Centauri B, the second sun, sweeping past every 80 years or so. That second star's gravity would constantly try to disturb the planet's orbit, to stretch it, to tilt it, and in some cases, to fling the planet right out of the system entirely. To picture the situation, imagine trying to keep a marble rolling in a steady circle around a post, while a second, heavier post keeps swinging past nearby, its own gravity yanking at the marble each time it approaches. Depending on how far out the marble is circling, it might hold its path, or it might be pulled into a wild, unstable trajectory and eventually thrown clear. The same logic applies to planets around Alpha Centauri A. Close into the star, a planet is held firmly in the grip of its own sun, relatively safe from the disturbing pull of the second star far away. Farther out, the influence of the companion star grows stronger, until eventually there is a boundary beyond which no stable orbit can exist at all, a region where any planet would inevitably be disrupted and lost. This means there is only a limited zone around Alpha Centauri A where a planet can survive for the long haul, a band close enough to the star to remain firmly bound. Remarkably, the habitable zone of Alpha Centauri A falls within that stable region. In other words, there is room, gravitationally speaking, for a planet to exist in the temperate zone around this star without being torn away by its companion. This is a crucial point, because it means the candidate planet is not asking us to believe in something impossible. The very orbit it would need to occupy, in the habitable zone, on a stable path, is exactly the kind of orbit that the gravitational arithmetic of this double star system allows. Nature has left a window open, a band of stable space in just the right place, and the candidate planet appears to sit within it. So not every orbit is possible. Only certain paths would be stable enough for a planet to survive over billions of years without being torn away. The team used this fact as a filter. They simulated millions of possible orbits, every reasonable path a planet might take around Alpha Centauri A. To understand the power of this approach, it helps to appreciate what a simulation like this actually does. The team could not see the planet's orbit directly. They had only a handful of snapshots, scattered across 6 years, 2 where something appeared and 2 where nothing did. That is precious little to work with. So instead of trying to draw a single orbit from those few points, they turned the problem around. They generated millions of hypothetical planets, each on a different orbit, with different shapes, different tilts, different distances from the star, different positions along their paths. Then they let the laws of gravity and geometry play out for each one. For every imagined planet, they could calculate exactly where it would have appeared in August of 2024, where it would have been in 2019, and where it would have sat in February and April of 2025. Then they compared those predictions against what Webb had actually seen and not seen. Most of the imagined orbits could be thrown out immediately. Some would have placed the planet in plain view during the very observations where nothing appeared, contradicting the data. Others would have been gravitationally unstable, doomed to be flung out of the system by the second star long ago, meaning no planet could survive on them in the first place. But a subset of orbits survived every test. These were the paths that put the planet exactly where it was seen when it was seen, and exactly where it would be hidden when it was not. For each one, they asked a series of questions. Would this orbit be stable in the presence of the second star, or would the planet eventually be ejected? Would this orbit place the planet where Webb saw it in 2024? Would it match the faint hint from 2019? And, crucially, would it explain why the planet was invisible in February and April of 2025? They were essentially asking the data to tell them a consistent story. Not just any planet, but a specific planet, on a specific path, that could account for every single observation, including the ones where it was not seen, and the results were striking. The simulations revealed that a large fraction of the stable orbits, roughly half of them, would have carried the planet too close to the star to be visible in those early 2025 observations. In other words, the disappearance was not only possible, it was expected. If the planet existed on one of these plausible orbits, then, in February and April of 2025, it would have been swinging through the part of its path where it nearly grazes the star from our viewpoint, hidden in the glare, exactly as observed. The non-detections were not evidence against the planet. They were, in their own strange way, consistent with it. This is a genuinely elegant result, and it is worth pausing to appreciate why. Imagine you had only the two non-detections and nothing else. You would conclude there was no planet. Now imagine you had only the two sightings and nothing else. You would conclude there probably was one, though you could not be sure. The power comes from combining all four observations and asking whether a single, consistent story can account for every one of them. And the simulation showed that yes, a single planet on a stable, elliptical orbit could appear in 2019, appear again in 2024, and then duck behind the glare of its star during both 2025 attempts. The four scattered observations, two positive and two negative, snap together into one coherent picture. That coherence is what gives the candidate its strength. It is not just that a planet might be there. It is that a specific planet, on a specific path, can explain absolutely everything we have seen and not seen across 6 years and 2 different telescopes. A picture began to emerge from all of this. A picture of a single, plausible world that could tie together 4 separate observations spanning 6 years. According to the models, this candidate planet would be a gas giant. Not a small, rocky world like Earth, but a large ball of gas, roughly the mass of Saturn. To picture what that means, think of Saturn itself, the ringed jewel of our own solar system. It is a world so large that more than 700 Earths could fit inside it, and yet it is made mostly of light gases, hydrogen, and helium. Wrapped around a relatively small core, it has no solid surface to stand on. If you tried to land on it, you would simply sink deeper and deeper into thickening layers of gas, the pressure and heat rising around you, until you were crushed long before you ever reached anything solid. A planet like that, orbiting Alpha Centauri A, would be a giant, swirling sphere of atmosphere, banded with clouds, churning with storms, beautiful and utterly inhospitable to anything resembling life as we know it. It would orbit Alpha Centauri A on an elongated, elliptical path, not a tidy circle but a stretched oval, swinging closer to the star and then farther away over the course of its year. That distance would vary between roughly 1 and 2 times the gap between Earth and our Sun. A single trip around its star would take somewhere between about 1.5 and 2.5 Earth years. That elliptical, stretched-out orbit is itself an important clue, and a likely reason the planet proved so elusive. A planet on a perfect circle stays at a roughly constant distance from its star, neither approaching nor receding. But a planet on a stretched ellipse spends part of its orbit swinging out wide, far from the star's glare, where it would be relatively easy to see. And it spends another part of its orbit diving in close, plunging toward the star, where it would vanish into the very brilliance the coronagraph is fighting to suppress. If the candidate planet is on such a path, then its visibility would come and go as it travels, easy to catch when it swings wide, impossible to spot when it dives in. That is exactly the behavior the observations seem to show. It is a satisfying fit between the shape of the orbit and the pattern of appearances and disappearances. A planet on a stretched, elliptical path would naturally be a part-time visitor to our telescopes, present for a stretch of its orbit and absent for another, exactly the kind of intermittent presence that the 4 observations sketched out. The very elusiveness that made the planet so frustrating to confirm turns out to be a clue to the kind of orbit it travels. In a way, the disappearing act is not a contradiction of the planet's existence, but a fingerprint of its path, the signature of a world on a long, looping journey around its star. And here is the detail that makes this candidate so remarkable. That orbit would place it within the habitable zone of Alpha Centauri A. The habitable zone is the band of space around a star where temperatures are just right for liquid water to exist on a surface. Not so close that water boils away, not so far that it freezes solid, the narrow, precious region where a world could, in principle, hold oceans. Every star has such a zone, but its location depends on the star's warmth. Around a small, cool red dwarf, the habitable zone huddles in close, a tight band near the dim star. Around a hot, brilliant star, it is pushed far out into the cold. And around a star like Alpha Centauri A, which so closely matches our own sun, the habitable zone sits at almost exactly the same distance as it does in our solar system, roughly the same region where Earth peacefully orbits, bathed in the gentle warmth that has allowed oceans and life to flourish here for billions of years. And this candidate planet sits squarely within that zone, around a star that is almost a twin of our own sun. If confirmed, it would be the closest planet to Earth ever found orbiting in the habitable zone of a sun-like star. That phrase deserves to be repeated, because it carries enormous weight. The closest planet to Earth in the habitable zone of a star like our Sun. For anyone who has ever wondered whether there might be another place out there, not impossibly far away, where the conditions for life might exist, this is about as close as the dream has ever come to the doorstep. There is another distinction this world would hold, if it is real. It would be the closest planet to its host star ever captured in a direct image. Most directly imaged planets discovered so far orbit far out from their stars, at great distances where the contrast between planet and star is more forgiving and the two are easier to separate. This candidate, by contrast, orbits relatively close in, deep inside the habitable zone, right up against the glare of its star, exactly the region that is hardest to probe. To capture a planet there, so near to its star, would be a genuine milestone for the art of direct imaging. It would also be, remarkably, the first planet imaged around a star that matches the Sun in both age and temperature, a true peer of our own solar system, seen directly for the first time. But there is an important catch, and honesty demands that we face it directly. This candidate planet, if it is real, is a gas giant. It is not a rocky world, with a solid surface where oceans could pool and life as we understand it might take hold. It is more like Saturn or Jupiter, a vast envelope of gas with no firm ground to stand on. So even though it sits in the habitable zone, the planet itself would almost certainly not be able to support life as we know it. A gas giant is the wrong kind of world for that. This is an important distinction that often gets blurred. The habitable zone is defined purely by distance and temperature, the region around a star where a world could hold liquid water on its surface if it had a surface and the right conditions. But sitting in the habitable zone does not make a planet habitable. It only means the planet is at the right distance for the right temperature. A gas giant in the habitable zone is still a gas giant, a vast ball of hydrogen and helium with no solid ground, no place for oceans to gather, no surface for life to take hold. Being in the right neighborhood is not the same as being the right kind of home. So we must be careful not to let the phrase habitable zone mislead us into imagining a second Earth. What the candidate offers is not a living world, but something almost as tantalizing. The possibility of the right conditions in the right place, around the right kind of star. Even if the planet itself is the wrong kind of world to use them. And yet, even this comes with a fascinating twist. Because in our own solar system, the giant planets are surrounded by entire families of moons. Saturn alone has dozens of them, some of which have become some of the most intriguing places in the search for life. If a Saturn-sized planet really does orbit in the habitable zone of Alpha Centauri A, then any large moons circling that planet would also be in the habitable zone. And a moon, unlike its gas giant parent, could potentially have a solid surface. It could have rock and ice and, conceivably, liquid water. We have a powerful example of this possibility right in our own backyard. In our solar system, the giant planets are circled by moons that have become some of the most exciting places in the entire search for life beyond Earth. One of Saturn's moons hides a vast ocean of liquid water beneath a shell of ice, and has even been seen venting plumes of that water into space. One of Jupiter's moons is thought to hold more water beneath its frozen crust than exists in all of Earth's oceans combined. These are not warm, sunlit oceans, but they are oceans nonetheless, kept liquid by the gravitational kneading of their giant host planets. Now imagine a moon like that, but orbiting a gas giant that itself sits in the gentle warmth of a habitable zone, around a star like our Sun. Such a moon could, in principle, enjoy both the steady warmth of its star and the comfortable conditions for liquid water on an actual surface. It is pure speculation, of course. We have no evidence whatsoever that such moons exist, but the very possibility is enough to make the imagination race. A warm gas giant orbiting our nearest solar twin, possibly cradling moons in the one zone around the star where surfaces could stay temperate. Science fiction has dreamed of exactly this for a long time. In fact, one of the most famous fictional worlds ever imagined, a lush green moon in a far-off film, was placed in orbit around a gas giant circling Alpha Centauri A. For years, that was pure invention, a storyteller's choice to set an imagined paradise around the nearest sun-like star, precisely because it was the nearest and felt the most reachable. There was no evidence at all that any such gas giant existed. It was simply a beautiful idea, a moon of forests and floating mountains orbiting a giant planet in our closest stellar neighbor. And now, decades later, reality has produced a candidate gas giant in almost exactly the place fiction imagined one, orbiting Alpha Centauri A in its habitable zone. The parallel is striking and more than a little eerie. It is, of course, only a coincidence. A case of imagination happening to land near where nature may actually have placed a world. But it is the kind of coincidence that captures the imagination, a reminder of how often human dreams and cosmic reality seem to circle the same ideas. Now reality is gesturing, faintly and uncertainly, in a direction that fiction reached long ago. But before anyone gets carried away, it is worth stepping back and being very clear about what we actually have here and what we do not. We do not have a confirmed planet. We have a candidate. A strong one. The strongest evidence yet for a world orbiting Alpha Centauri A, but a candidate nonetheless. It is worth being precise about what that word means, because in everyday language a candidate sounds almost like a near certainty, and in science it means something more cautious. A candidate is a signal that looks like what we are searching for, that has passed some tests, but that has not yet been confirmed beyond reasonable doubt. It is a promising lead, not a settled fact. History is full of candidates that became confirmed discoveries, and equally full of candidates that quietly faded away once more data arrived. Calling this a candidate is not a way of downplaying it. It is a way of being honest about exactly where it stands. A serious result that has earned attention but not yet earned certainty. The evidence is genuinely compelling. A direct point of light in 2024. A matching hint from 2019. A set of simulations showing that a single stable orbit can explain all 4 observations, including the 2 where nothing was seen. That is a real, serious case. The team did an enormous amount of careful work to rule out the obvious alternatives. They checked whether the point of light could be a distant background galaxy that happened to lie behind the star, and weighed that against the evidence. They considered whether it could be a passing object in our own solar system, drifting through the field at the wrong moment. They examined whether it might be an artifact of the telescope or the image processing, a leftover speckle masquerading as a world. They even placed tight limits on the amount of dust in the system, ruling out the idea that the planet's disappearance could be explained by some obscuring cloud rather than by orbital motion. In other words, they did not simply find a promising signal and declare victory. They interrogated it from every angle they could think of, trying to break their own result, and it survived that scrutiny well enough to be published as the strongest evidence yet for a planet around Alpha Centauri A. It is enough to be published in respected scientific journals, enough to capture the attention of astronomers around the world. But it is not yet certainty. 2 of the 4 observations were non-detections. The interpretation that ties everything together, while elegant and plausible, still rests on the assumption that the planet simply moved out of view at the wrong moments. That is a reasonable assumption, supported by the orbital models, but it is still an assumption. In science, the line between a candidate and a confirmed discovery is sacred. You do not cross it on the strength of a compelling story alone. You cross it when the evidence becomes so overwhelming that no other explanation can survive. And we are not there yet with this world. This is, in fact, one of the most important things to understand about how science actually works. It is not a parade of triumphant certainties. It is a slow, careful, sometimes frustrating process of building a case, piece by piece, while constantly trying to prove yourself wrong. The popular image of a scientist is someone who makes bold pronouncements and defends them. The reality is almost the opposite. The best scientists are their own harshest critics, forever poking holes in their own ideas, forever asking what they might have missed. A result is not trusted because someone clever announced it. It is trusted because it has been attacked, again and again, from every angle, and has refused to break. That adversarial process, where each claim must survive relentless scrutiny, is what gives science its extraordinary power to find the truth. It is slow, and it is humbling, and it offers few of the clean, dramatic moments we might wish for. But it works. precisely because it refuses to let wishful thinking stand in for evidence. The team behind this discovery did not simply announce a planet and celebrate. They went back again and again, knowing that each new observation might destroy their own result. When the planet failed to appear, they did not bury the bad news. They placed it front and center, and then did the hard work of figuring out whether it could be reconciled with the original detection. That willingness to confront the inconvenient data, to treat a disappearance as a puzzle rather than an embarrassment, is exactly what separates careful science from wishful thinking. There is a deeper lesson hidden in all of this, one that goes well beyond Alpha Centauri. The public often imagines science as a collection of certainties, a list of facts handed down from authorities in white coats. But that is not what science actually is. Science is a method, a way of interrogating reality that is built, at its core, around doubt. A good scientist does not fall in love with an idea and defend it at all costs. A good scientist takes their most cherished result and attacks it, hunting for every possible way it could be wrong, every alternative explanation, every hidden flaw. Only when an idea has survived that relentless assault does it begin to earn trust. The story of the disappearing planet is a textbook example of this method in action. The team had a thrilling result in 2024, a direct image of a possible planet next to the nearest sun-like star. They could have rushed to announce a triumphant discovery. Instead, they went back to check, knowing that the universe owed them nothing, knowing that the planet might fail to reappear. And when it did fail to reappear, twice, they did not hide it. They built it into the heart of their analysis and asked whether the disappearances could be reconciled with the original detection. The answer they found, that a single plausible orbit could explain all 4 observations, is genuinely compelling. But they were careful to call it what it is, a candidate, not a confirmed world. The story of the disappearing planet is, in many ways, a story about scientific honesty. It would have been easy and tempting to publish the dramatic detection from 2024 and stay quiet about the later non-detections. Instead, the whole messy, complicated picture was laid out in the open, with all its uncertainty intact. And that is precisely what makes the case so credible. Now, it is worth pausing to appreciate just how hard it was to get even this far. Consider what Webb actually accomplished here. It pointed itself at a pair of stars so bright they threatened to overwhelm its instruments. It blocked out the glare of one of them with a tiny mask, holding that mask in position with breathtaking precision across millions of kilometers of empty space. It captured the faint infrared heat glow of an object billions of times dimmer than the star beside it. And it did all of this for a target that moves quickly across the sky, requiring a custom observing sequence designed specifically for this one system. These were among the most demanding observations the coronagraph had ever been pushed to make. Step back and think about the chain of human achievement that made this single faint point of light possible. Generations of physicists worked out how light behaves, how it bends and interferes, so that engineers could design optics capable of suppressing a star's glare. Decades of engineering produced a telescope that could be folded into a rocket, flung beyond the moon, unfolded in the dark, and chilled to within a few degrees of the coldest temperature in nature. Teams of specialists invented the methods to subtract the telescope's own fingerprint from its images, separating real signals from instrumental ghosts. And then, a dedicated group designed a one-of-a-kind observing strategy for the single most stubborn nearby target in the sky. All of that, the physics, the engineering, the software, the years of planning, converged on one purpose: to pull a whisper of light out of an overwhelming glare, 4 light-years away. The very fact that a single point of light emerged at all, and that it lined up with an earlier independent hint from a completely different telescope is a triumph of engineering and patience, regardless of whether the planet is ultimately confirmed. We are, quite literally, at the edge of what our technology can currently do. Looking into the glare of our nearest stellar neighbor and trying to pick out a faint world hidden in the light. A generation ago, this would have been pure fantasy. Now it is a published scientific result, complete with orbital models and journal papers. That alone is worth marveling at. There is something humbling, too, about the timescales involved in a discovery like this. The candidate planet, if it exists, has been orbiting Alpha Centauri A for billions of years, completing one slow loop after another, long before any human being existed to wonder about it. The light we are now studying left the system more than 4 years ago, while we went about our daily lives, utterly unaware. The faint hint from 2019 and the detection from 2024 are separated by years, and the work of tying them together stretched across still more time, demanding patience at every step. This is the rhythm of astronomy. It does not move at the pace of human impatience. It moves at the pace of orbits and light, of careful observation and slow confirmation, of results that take years or decades to firm up. A planet that takes between about 1.5 and 2.5 years to circle its star cannot be rushed. We simply have to wait for it to come back around into view. In an age that prizes instant answers, there is something almost meditative about a science that asks us to wait, to watch, to return again and again to the same patch of sky over many years, slowly assembling the truth, one observation at a time. The story of the disappearing planet is not finished, and it may not be finished for years to come. That is not a flaw in the science. It is simply the nature of looking out across such vast distances, at objects so faint and so far away. But the team is not satisfied with a candidate. They want certainty, and so the search continues. The plan now is to return to Alpha Centauri again with Webb, watching and waiting for the moment when the planet, if it exists, swings back out into a part of its orbit where it can be seen once more. There is a certain drama in this waiting. The planet, if it is real, is out there right now, moving along its slow, elliptical path, sometimes hidden in the glare, sometimes swinging wide into view. Astronomers are essentially lying in wait, watching for the right moment, the window when the planet pulls far enough from its star to be captured cleanly once again. When that window comes, Webb will be ready, its golden eye trained on our nearest neighbor, hoping to catch the elusive point of light a second time and pin it to its predicted place. It is a patient hunt, governed by the slow clock of a planetary orbit, and it may take time before the geometry is right. But each opportunity carries the chance to transform the story, to turn a tantalizing maybe into a confirmed discovery. If the orbital models are right, there will be windows of opportunity, stretches of time when the planet pulls far enough away from the star's glare to be captured cleanly. Catch it in one of those windows, confirm that it sits exactly where the models predict, and the case for a real planet would become dramatically stronger. This is the beautiful thing about a good model. It does not just explain what has already been seen. It makes predictions about what will be seen in the future. The orbital simulations do not merely tie together the past observations. They forecast where the planet should appear at specific times yet to come, if it truly exists on one of those stable, consistent orbits. That turns the next round of observations into a genuine test. If astronomers point Webb at Alpha Centauri during a predicted visibility window and find the planet sitting right where the model said it would be, that would be powerful confirmation. It would mean the model is not just a clever story spun to fit the data, but a real description of a real world following a real path. And if the planet is not there, if the window comes and the spot is empty, that too would be informative, forcing a rethink of whether the candidate is genuine at all. Either way, the predictions sharpen the search, transforming a frustrating game of hide-and-seek into a structured, testable investigation. A second clean detection, in the right place, at the right time, would transform this from a tantalizing candidate into a genuine discovery. And Webb is not the only tool that will join the hunt. A new telescope is on the way, one specifically suited to chase down exactly this kind of target. The Nancy Grace Roman Space Telescope is scheduled to launch in the coming years, and it carries dedicated technology designed to study binary star systems like Alpha Centauri. It is built to test new techniques for blocking starlight and revealing faint planets hidden in the glare. Roman represents the next step in a long lineage of planet-hunting instruments, each one more capable than the last. It carries an advanced instrument specifically designed to suppress starlight with even greater precision than before. A technology demonstration meant to pave the way for future telescopes that could one day directly image small, rocky, Earth-like worlds around other stars. Alpha Centauri, as the nearest and most accessible Sun-like system, is a natural proving ground for these techniques. Crucially, Roman will observe in visible light, while Webb sees in the infrared. That difference matters enormously. By combining what the two telescopes see across different kinds of light, astronomers could learn things about this candidate world that neither telescope could reveal alone. Webb's infrared view reveals the planet's heat. Roman's visible light view could reveal how much starlight the planet reflects, offering clues about its size and the nature of its clouds and atmosphere. Think of it like examining an object under two completely different kinds of illumination. One reveals the warmth it gives off, the glow of its own internal heat. The other reveals how it reflects the light that falls on it, its color, its brightness, its texture. Each kind of light tells a different part of the story, and only by combining them can you build a complete portrait. A planet that is merely a faint smudge to one telescope might become a richly detailed world when seen through the combined eyes of two. Put the two together, and a blurry candidate could slowly resolve into a real, characterized world, with measured properties and a known orbit. This is how the deepest discoveries in astronomy usually happen. Not in a single flash of revelation, but through the patient combination of many instruments, many observations, and many years of careful work, each one adding another piece to the puzzle until the picture finally becomes undeniable. If this planet is confirmed, the implications would ripple far beyond the simple fact of its existence. A single confirmed world, in the right place, can carry meaning out of all proportion to its size. This one would touch several of the deepest questions in modern astronomy at once: how planets form, where they can survive, how common other worlds really are, and how close the nearest one might be. For one thing, it would challenge our understanding of how planets form and survive. Remember, Alpha Centauri is a system with two closely orbiting Sun-like stars. For a long time, many scientists assumed that such a chaotic gravitational environment would be hostile to planet formation. The constant tug of a second star, sweeping past every few decades, seemed likely to disrupt the delicate disks of gas and dust from which planets are born, scattering the building blocks before they could ever assemble into worlds. A confirmed gas giant in this system would tell us that planets can form and endure even in these turbulent, double-sunned environments. To appreciate why this matters, it helps to understand how planets are thought to be born. When a star forms, it does not form alone. It emerges from a vast, collapsing cloud of gas and dust. And as the young star ignites at the center, the leftover material settles into a flattened, spinning disk around it. Within that disk, tiny grains of dust begin to stick together, building up over time into pebbles, then boulders, then bodies the size of mountains, and eventually into full-grown planets. It is a slow, delicate process, requiring a relatively calm and stable disk that can survive for millions of years while planets gradually assemble. Now introduce a second star into that picture. A nearby companion star, sweeping past every few decades, would tug at the disk with its gravity, stirring it, heating it, potentially flinging material outward and disrupting the gentle accumulation of planetary building blocks. For a long time, it was natural to assume that such interference would make planet formation difficult or even impossible in tightly bound double star systems. The disk would be too disturbed, too short-lived, too chaotic for planets to come together. A confirmed planet around Alpha Centauri A would overturn that assumption. It would tell us that nature finds a way, that planets can assemble and survive even amid the gravitational turbulence of two closely orbiting stars. That would be a profound lesson, because binary and multiple star systems are extremely common throughout the galaxy. A huge fraction of all the stars in the Milky Way have at least one companion. When we picture a typical star, we tend to imagine something like our own sun, a single star traveling alone through space with its family of planets. But our sun may actually be in the minority. A very large share of the stars in our galaxy come in pairs, or in groups of 3 or more, bound together by gravity into systems with 2 suns, 3 suns, sometimes even more. For a long time, the prevalence of these multiple star systems cast a shadow over the search for other worlds. If planets struggled to form or survive around closely bound stars, then a huge fraction of the galaxy's stars would be off the table, unable to host the stable, long-lived worlds that life might need. The galaxy's potential for planets and for life would be dramatically reduced. But if planets can form and persist even in a system like Alpha Centauri, with 2 sun-like stars orbiting closely together, then that shadow lifts. If planets can thrive even in tightly packed double star systems, then the number of possible worlds in our galaxy grows dramatically. The places where planets might exist would expand to include vast populations of stars we might otherwise have written off as too chaotic. In other words, a single confirmed planet around Alpha Centauri A would not just be one more dot on the map. It would reshape our sense of how and where planets can exist at all. It would tell us that the galaxy is even richer in worlds than we already believed, that planets crowd not only the calm single stars but the turbulent double star systems too, that the places where worlds can take root are more numerous and more varied than we had dared assume. Each such revelation widens the canvas on which the story of planets, and possibly of life, can play out. And there is the matter of proximity, which changes everything about what we could do next. Almost every exoplanet we have ever found is hopelessly far away. So distant that we can study them only in the most limited ways, gathering faint scraps of data and stretching them as far as they will go. Distances of hundreds or thousands of light years are the norm in the catalog of known worlds, and at such distances, even our finest instruments can extract only the barest details. A planet that far away is, in practice, forever beyond our reach for close study. A number in a database more than a place we can examine. But a planet around Alpha Centauri would be different. It would be the closest such world we could possibly study. Its nearness would make it, by far, the best opportunity we have ever had to collect detailed information about a planetary system other than our own. Almost everything we know about planets around other stars comes from objects so distant that they are little more than faint signals, dips in starlight or tiny wobbles, stretched and squeezed for every drop of information we can extract. We rarely get to truly examine these worlds. They are too far, too faint, too lost in the vastness. But a planet at Alpha Centauri would be the great exception. It would be close enough that future telescopes, more powerful than anything we have today, could study it in genuine depth, not as a distant abstraction, but as a real, specific world with measurable properties. It would become the natural target for every new instrument and technique, the first place we would point our growing capabilities, the testing ground for our deepest questions about other planetary systems. In the search for worlds beyond our own, proximity is everything. A planet 1,000 light-years away might be scientifically interesting, but a planet 4 light-years away is something else entirely, a neighbor we could come to know. We could, in time, study its atmosphere, its composition, its weather, its moons if it has any. We could turn the full force of our growing telescope technology on a single, nearby world and learn it intimately, in a way that is simply impossible for planets hundreds or thousands of light-years away. Consider what that intimacy could mean. For a distant exoplanet, we are often lucky to learn just its size and its orbit, the barest outline of a world. But for something as close as Alpha Centauri, future instruments could go far deeper. By carefully analyzing the light from the planet, astronomers could begin to read the composition of its atmosphere, identifying the gases that swirl within it. Light carries hidden information. When light from a planet passes through or rises out of its atmosphere, the gases there absorb certain colors and let others pass, leaving a pattern of dark gaps in the spectrum, a kind of barcode unique to each substance. By spreading the planet's light out and reading that barcode, astronomers can determine what the atmosphere is made of: water vapor, carbon dioxide, methane, and more, each leaving its own telltale signature. For a planet as close as Alpha Centauri, future instruments could read these signatures with a clarity impossible for more distant worlds. They could track changes over time, watching weather patterns shift, watching the planet brighten and dim as different faces turn toward us. They could measure its temperature, map its clouds, and perhaps, with future generations of telescopes, even search any moons it might have for signs of conditions friendly to life. A nearby world is not just a dot to be confirmed and catalogued. It is a place that can be studied, returned to, examined again and again as our tools improve. It becomes a long-term companion in our exploration, a fixed point we can keep coming back to for decades, even centuries. This is why astronomers care so deeply about this faint, flickering, disappearing point of light. It is not merely that a planet might exist around Alpha Centauri A. It is that, if it does, it would be the one planet beyond our solar system that we could come to know better than any other. Out of nearly 6,000 known worlds, almost all of them remain forever out of reach. Distant points we can characterize only in the broadest strokes. But this one, our nearest possible neighbor, could become the exception. The world we study in depth, return to again and again, and slowly come to understand as a real, particular place rather than a faint statistic. That is what gives this faint, troublesome point of light its outsized importance. It is not just another candidate among thousands. It is potentially the closest, most studiable world we will ever find, the one that could open a window onto a planetary system other than our own. A laboratory next door. A second planetary system, close enough to truly examine. And there is a larger significance to the method itself, beyond this one planet. Direct imaging, Actually capturing the light of a planet rather than inferring it indirectly is widely seen as the key to the future of the search for life. The indirect methods that have found most of our planets are powerful, but they have limits. They can tell us that a planet exists, how big it is, how massive it is, how long it takes to orbit. But to truly probe a world, to ask whether its atmosphere holds the chemical signatures that might hint at life, it helps enormously to capture the planet's own light directly and spread it out into a spectrum, reading the fingerprints of the gases within it. That is far easier to do for a planet whose light you can actually isolate, separate from the glare of its star. And it is easier still for a planet that is close, Alpha Centauri, as the nearest system of all, is the ideal place to develop and perfect these techniques. Every lesson learned here, every method refined in the brutal glare of these two bright stars, will carry forward to the search for smaller, rockier, more Earth-like worlds around other stars. In this sense, the effort to image a planet at Alpha Centauri is not just about Alpha Centauri. It is about learning to see planets at all, building the skills and the tools that future astronomers will use to search for living worlds across the galaxy. This candidate, elusive as it is a proving ground for the whole grand endeavor. And in the longest run of all, there is the dream that has haunted humanity since we first understood what stars really are. The dream of going there. For as long as humans have understood that the stars are other suns, scattered across unimaginable distances, we have wondered whether we could ever cross the gulf between them. It is one of the oldest yearnings woven into our species, the urge to see what lies beyond the next horizon, to cross the next ocean, to set foot on the next shore. The stars are simply the farthest horizon of all, and Alpha Centauri is the nearest point on it. Alpha Centauri has always been the natural first destination for any imagined interstellar journey, precisely because it is the closest. If there is a planet there, in the habitable zone of a sun-like star, then that dream gains a destination, a specific place to point our hopes. We are nowhere near capable of such a voyage today. The distances involved are almost beyond comprehension, and the technology to cross them does not yet exist. But people have thought seriously about how it might one day be done. The fundamental obstacle is speed. With conventional rockets, burning fuel to push themselves forward, a journey to Alpha Centauri would take tens of thousands of years, far longer than civilizations tend to last. To make the trip in a human-relevant span of time, you would need to travel at a substantial fraction of the speed of light. And reaching such speeds is extraordinarily difficult. The energy required is staggering, and the engineering challenges are immense. One idea that has been seriously explored involves doing away with onboard fuel almost entirely. Instead of carrying heavy tanks of propellant, you build a spacecraft that is astonishingly small and light, little more than a tiny chip attached to a thin, reflective sail. Then, from back home, you aim a powerful array of lasers at that sail, pushing it with the gentle but relentless pressure of light itself. With no heavy fuel to carry and a continuous push from the lasers, such a feather-light craft could, in principle, be accelerated to a fraction of the speed of light, completing the journey to Alpha Centauri not in tens of thousands of years, but in mere decades. It is a beautiful idea, though it remains far beyond our current abilities, riddled with enormous technical hurdles. The challenges are daunting, building lasers of staggering power, crafting sails light enough and tough enough to survive the acceleration, finding ways to gather information from a craft so tiny and send it back across 4 light-years of space. Even if such a probe could be launched, it would still take decades to make the journey, and decades more for its faint signals to crawl back to Earth at the speed of light. A mission like that would span generations, begun by people who would never live to see its results, carried forward by those who came after. It is a humbling thought, and also an inspiring one. The idea that we might one day reach across the void to our nearest neighbor, not in a single lifetime, but as a gift passed down through the long relay of human curiosity. But the very fact that serious people are studying such concepts tells you something about the pull this star system exerts on the human imagination. Of all the places in the universe we might dream of reaching, Alpha Centauri is the one that feels almost, just almost, within the reach of a sufficiently determined future. And if we knew there was a world there, a real planet waiting at the end of that impossible journey, the motivation to attempt it would only grow. A destination changes everything. It is one thing to dream of traveling to a distant star simply to be there. It is another to know that a planet circles that star, a place with its own weather, its own moons, its own unrepeatable character, waiting across the dark. A star alone is a light to admire. A star with a world is a destination to reach, a place that could, in the wildest imaginings of the future, be explored, mapped, perhaps even seen up close by some far-off probe or some distant generation. The presence of a world transforms the meaning of the journey, giving it not just a direction, but a purpose. Not just a point of light to aim for, but a place to arrive. We are nowhere near capable of such a voyage today. But knowing that a world might be waiting there, knowing that the nearest sun-like star might host a planet of its own, transforms Alpha Centauri from an abstract point of light into a place. A real place, with a real world, that future generations might one day study up close, and perhaps, in some unimaginably distant future, reach. For now, though, we are left with the mystery. There is something larger at stake in all of this. Something that reaches beyond the technical question of whether one particular planet exists. For all of human history, we have wondered whether we are alone. Whether the Earth is a singular accident, a one-of-a-kind cradle of life in an otherwise empty cosmos, or whether the universe is filled with worlds, some of them perhaps stirring with life of their own. For most of that history, the question was unanswerable. We had a sample size of one planet known to harbor life, one example to reason from, and no way to know whether it was typical or unique. But every discovery like this one chips away at our isolation, not by finding life, but by finding the places where life might be possible. Each new world around, each new star, expands our sense of what exists out there. And a world around Alpha Centauri would carry a special weight in this story, because it is so close. It would tell us that planets are not just scattered across the distant reaches of the galaxy, but that they cluster right around us, in the very nearest systems, around the very nearest sun-like stars. It would suggest that wherever we look, even on our own doorstep, worlds are waiting. And if worlds are everywhere, then the conditions for life, whatever they may require, have countless places to arise. We still do not know how rare or how common life truly is. We know it happened at least once, here, on our own world. But we do not yet know whether that was a near miracle, a fluke that almost never occurs, or something that springs up readily wherever the conditions are right. The more worlds we find, the more chances the universe has had to answer that question in places we cannot yet see. Every new planet is another roll of the cosmic dice, another stage on which the story of life might or might not have begun. A planet around Alpha Centauri would not tell us whether life is out there, but it would remind us, vividly, that the stage is vast and that the number of places where the experiment of life could have run is almost beyond imagining. This does not prove that we have neighbors. It does not tell us that life is common or that it is rare. But it changes the texture of the question. It moves us from a universe that seems empty by default to a universe that seems crowded with possibility, full of worlds we are only just beginning to see. The candidate planet at Alpha Centauri, whatever it turns out to be, is a small but profound reminder that the cosmos is not a barren void with a single inhabited speck. It is a place teeming with worlds, and we are surrounded by them, even at the very edge of our own cosmic neighborhood. Look up at the night sky, and almost every point of light you see is a star, and around a great many of those stars, we now know, planets are turning. The darkness between the stars is not empty in the way it once seemed. It is dotted everywhere, with worlds we are only beginning to detect, each one a place with its own story, its own conditions, its own unrepeatable history. And the very nearest of those points of light, the golden one low in the southern sky, may be turning a world of its own as well. That is a different kind of universe to live in than the lonely one our ancestors imagined. For most of human history, people pictured the Earth as the center of everything, a unique stage set apart from the lights in the sky. Then, slowly, we learned otherwise. We learned that the sun is a star, and the stars are other suns. We learned that our sun is one of hundreds of billions in our galaxy, and our galaxy one of hundreds of billions in the universe. And now we are learning that those countless stars are accompanied by countless worlds, that planets are not rare jewels but common features, scattered through the cosmos in numbers beyond counting. Each step in that journey has moved us further from the center and deeper into a vast, populated cosmos. The candidate at Alpha Centauri is the latest step, bringing the lesson home in the most literal way, by suggesting that even the nearest sun-like star may have a world of its own. We are not perched alone on a singular island. We are one world among a multitude, in a universe that seems, the more we look, to be filled with places. And it is a universe we are still only beginning to map. And so, we return to the heart of it all. A candidate planet that hides every time we try to pin it down, slipping back into the glare of its star as if it does not wish to be found. A Saturn-sized world, possibly orbiting our nearest solar twin, possibly in the habitable zone, possibly cradling moons we cannot yet imagine. So much possibility, and so little certainty. That is the honest state of things. Every part of the description carries that same word, possibly a planet, possibly in the habitable zone, possibly with moons. It is a portrait built entirely out of maybes, and yet it is the most concrete glimpse we have ever had of a world around the nearest sun-like star. That is the strange place we find ourselves in, holding a picture that is at once tantalizingly detailed and frustratingly uncertain, a world sketched in possibilities, waiting for reality to confirm or erase it. It is easy, in a story like this, to wish for a clean ending, to want the planet confirmed, the mystery solved, the question answered once and for all. But there is something fitting about the fact that the universe has not given us that satisfaction yet. Because this is what real exploration feels like. Not a tidy sequence of answers, but a long, patient negotiation with the unknown, full of false starts and disappearing clues and observations that refuse to behave. We tend to remember the great discoveries of science as clean, triumphant moments, a flag planted, a prize won, a fact established. But that is rarely how it actually happens. Behind almost every confirmed truth lies a messy, uncertain struggle. Years of ambiguous data and competing explanations and results that appear and vanish and appear again. The disappearing planet at Alpha Centauri is simply that struggle, caught in the act, unfolding in real time before our eyes. We are watching science as it actually is, not the polished version in the textbooks, but the raw, ongoing process of wrestling truth out of a reluctant universe. And there is a kind of beauty in that. In the willingness to sit with uncertainty, to say honestly that we do not yet know, to keep looking even when the answer refuses to come easily. The closest star system to Earth has guarded its secrets for the entire span of human history. It is not going to surrender them all at once. What Webb has given us is not a final answer, but a doorway. A first genuine look into the glare of our nearest neighbor, and a glimpse of something that might be waiting there. The point of light may yet vanish for good, exposed as a trick of noise and scattered starlight. Or it may return, again and again, until its presence becomes undeniable, and humanity adds a new world to the map, the closest sibling to Earth's own family of planets. We do not yet know which way the story will end, but we know this. For the first time, we have looked directly into the heart of Alpha Centauri and seen something there. Something faint, something elusive, something that may turn out to be the nearest planet to Earth orbiting a star like our own. And whatever it proves to be, the simple fact that we can now look at all, that we can aim a telescope at our closest stellar neighbor and pull a possible world out of the blinding light, is one of the quiet miracles of our age. A century ago, we did not even know that other galaxies existed beyond our own. Half a century ago, we had never confirmed a single planet around another sun-like star. A generation ago, directly photographing a planet next to a bright star was the stuff of dreams. And now, here we are, capturing a faint point of light beside the nearest solar twin, modeling its orbit, debating its moons, planning the next observation that might confirm it. The pace of discovery has been breathtaking, carrying us in a few short generations from near total ignorance about other worlds to standing at the threshold of imaging the planet next door. Think of the long road that led here. For thousands of years, Alpha Centauri was nothing but a bright point in the southern sky, a star and nothing more. Its true nature entirely hidden. Slowly, over generations, we learned that it was not one star but three. We measured its distance and discovered it was our nearest neighbor. We came to understand that it held two sun-like stars, the kind that could, in principle, shelter worlds. And now, in our own time, we have finally reached the point where we can look into its glare and ask directly whether such a world is there. Every generation added a piece. Every generation handed the question forward, a little better understood than before. And we are the generation that got to take the first real look. The people who first charted Alpha Centauri's position never knew it was a triple system. Those who discovered it was our nearest neighbor never had the tools to look for its planets. Those who first dreamed of worlds around other stars never lived to see a single one confirmed. Each of them carried the question as far as they could and then passed it on, trusting that someone, someday, would carry it further. We are the inheritors of all that effort, standing on the accumulated work of everyone who ever looked up at that golden point of light and wondered. It is a humbling inheritance, and a thrilling one, to be the ones holding the question at the very moment it begins, at last, to yield an answer. And in our time, with our telescopes, we have finally been able to do what all of them could only imagine, to look directly into the glare of our nearest neighbor and ask whether a world is hiding there. That is a remarkable place to stand in the long human story of looking up and wondering. The disappearing planet is still out there, somewhere in that distant glow, keeping its secret a little while longer. It has waited billions of years already, circling its star in patient silence, indifferent to whether we ever find it. The choice to keep looking is entirely ours, an act of curiosity and persistence in the face of a universe that gives up its answers slowly and on its own terms. And we will keep looking, patiently, until the nearest light in our southern sky finally tells us the truth. If this journey into the cosmos left you with a deeper sense of wonder, Take a moment to like the video and subscribe for more. And the next time you find yourself beneath a dark southern sky, look for that bright, golden point low along the Milky Way. And remember that somewhere in its glare, a world may be waiting for us to find it.